Alright, so in section 9.8, we are going to learn one last factoring strategy. Really, we've talked about what is called factoring by grouping before. We've used it while we've been factoring trinomials, but today we're going to look at how factoring by grouping can be applied in a different way. So previously, when we talked about factoring trinomials, you should all recognize the step that's currently on the screen in front of us. So we have that step where we look at terms in groups of pairs and we factor out their greatest common monomial. And so here we can see this looks very similar to a factoring trinomial problem we would potentially see. So here we have both 3x and 2 being multiplied by x plus 6. Both of those terms, 3x is being multiplied by the binomial x plus 6, and 2x is being multiplied by the binomial x plus 6. So we see this same binomial. As a result, we can group 3x and 2 together, because 3x and 2 are both being multiplied by x plus 6. So this strategy where we grouped things together, we pulled them out in front and said, well, both 3x and 2 are being multiplied by x plus 6. This step here is actually called factoring by grouping, and we're going to use it on the next few slides to factor different types of polynomials than we've seen before. Alright, so if you feel like you have a good handle on factoring by grouping, you can go ahead and rewrite the following polynomial expressions into factored form. If you aren't sure what to do or how to write these into factored form, just keep watching the video. So if I look at the first problem, what I notice is that both 2x and 4, both of those are being multiplied by x plus 6. So what I can do from here is I can group those together. I can say negative 2x plus 4. Negative 2x and 4 are both being multiplied by x plus 6. And so I group the negative 2x and 4 out in front because I know they're both being multiplied by x plus 6. And as a result, I've rewritten this polynomial expression into factored form. And then if I look at the second one, the first thing I notice is that I have a negative in front of that second binomial. And what that negative really is it is a negative 1 out in front of that second binomial. So what I know here is that both 4x and negative 1 are being multiplied by 3x minus 4. So I can group them together out in front. 4x and negative 1 are both being multiplied by 3x minus 4. And I have rewritten both of these polynomial expressions into factored form. Alright, so here's where we're going to expand this a little bit. What you'll notice here is that these polynomials look different than the polynomials we've seen before. First of all, you'll notice that each of them contain a variable that is going to the power of 3. So you can see that here we have x to the third power, a to the third power, and so far your first instinct has been to factor out a greatest common monomial among all of the factors, because you want to get that to be x squared over a squared. However, if you look here, the 15 and the 99 do not have a variable. So essentially what that tells us is we're not going to be able to factor out a greatest common monomial. So instead we have to look for other options. And my first option, because I know that I've seen things with 4 terms that I factored before, is to factor by grouping. So what I'm going to do here is I'm going to group these into pairs. So anytime you see 4 terms being added and you can't factor out a greatest common monomial, try factoring by grouping first. So here I look at x cubed and 3x squared. Those both contain an x squared, so I'm going to factor the x squared out in front. X cubed divided by x squared becomes x. 3x squared divided by x squared simply becomes 3. And then I look over here at the 5x and the 15, and I see they're both divisible by 5, so positive 5. And then I just have x plus 3. So what you can see here is that x squared and 5 are both being multiplied by an x plus 3. So what I can do is I can group x squared plus 5, and then say, well, both of those terms are being multiplied by x plus 3. So I've rewritten this into what looks like more like factored form. Now from here, my next question should always be, can I factor this further? And I notice that I have an x squared in there, but when I look at this x squared plus 5 part right here, I also notice that while x squared is a perfect square, 5 is not. So I cannot use one of my special patterns that I observed earlier this week to factor this polynomial further. However, if I look at my other strategies, my special patterns don't really apply, and neither does factoring a trinomial. So I can stop here. Now, if I look over at the second one, what I'll notice first is, again, I have that situation where I can't factor out a greatest common monomial. So instead, I'm going to look at this in pairs. So I look at the a cubed minus 11a squared, and I notice that they both contain an a squared. So I factor out an a squared. That becomes just a minus 11. And then I notice here that negative 9a plus 99, well, I know I'm trying to get a positive a inside the parentheses, so I'm going to factor out a negative 9. And as a result, I get a minus 11. And then I notice that these have the same binomial they are being multiplied by, so I can group the a squared minus 9 together, and both a squared and a negative 9 are being multiplied by a minus 11. Now, from here, it's my decision to decide whether or not I can factor this further. And if I look at the a squared minus 9, I know there's the potential that I could factor that further. And if I look here, I see one of my special properties taking place, because this is really a 1 out in front. The square root of 1a squared is just 1a. The square root of 9 is 3, and I see no middle term. So I know that I can factor this portion I've boxed in pink a little bit further. And I know that that piece factors to 1a plus 3 times 1a minus 3. And then I still have that a minus 11 at the end. So now this is written in complete factored form. I have exhausted and tried all of my strategies, and in this problem I used factoring by grouping, followed by a special pattern in order to write this into the fully factored form of a plus 3 times a minus 3 times a minus 11. And since this isn't set equal to anything, it's just an expression, I can't rewrite that any further, and I will not be solving for any values for a. I am just trying to rewrite it into factored form. Alright, so on the next two slides, you'll notice there are two factoring by grouping problems. What I would like you to do is pause the video, try these two on your own, and then check your answer. If you are completely lost, you are more than welcome to keep watching to watch a few more examples, but if you think you understand it, I'd like you to try it on your own. So as I look at this problem, I notice that I have 4 different terms, and that these 4 terms do not have a greatest common monomial that can be factored out. So I'm going to try to use factoring by grouping instead. So I'm going to group them into pairs. I can see here I have a cubed minus 3a squared. Both of those are divisible by a squared, so I factored out an a squared. So I end up with a minus 3. And then I know that I want to get a similar binomial piece here, so I'm going to factor out a negative 4, because that will change negative 4a divided by negative 4. That will become just a, and 12 divided by negative 4 becomes 3. So then I can see I have these same binomials being multiplied by a singular term. So now I can see I have a squared minus 4 and a squared and negative 4 are both being multiplied by a minus 3. So I've applied factoring by grouping here, and I've rewritten this polynomial expression into factored form. Now, from here, what I'm going to do is I'm going to see if I can factor this further. And what I notice here is that I have one of my special properties. If I take the square root of a squared, that is just a. And if I take the square root of 4, that is 2. So I know that I have 2 perfect squares involved here, and as a result I know that I can factor this further. I know that I have a minus 2 times a plus 2. I don't have a middle term, so I know that I have to have a positive and a negative, and then I keep in mind that my a minus 3 is still there. And then if I look, I don't have any more a squareds. They are all singular a's, so I know that this cannot be factored further. So again, we had a factoring by grouping problem paired then with one of our special properties that we discussed earlier this week. Alright, so final problem, and I first look at this problem and I notice that I don't have a single greatest common monomial that I can factor out in front. So again, I'm going to try factoring by grouping. So here I notice in this first pair that both a cubed and 6a squared are divisible by a squared. So I factor that a squared out in front. A cubed divided by a squared becomes a. 6a squared divided by a squared becomes 6. And then I look at this second chunk here. They are both divisible by negative 25. I know if I factor out a negative 25, I'll end up with a positive a, and then negative 150 divided by a negative 25 is a positive 6. Then from here I see that both a squared and negative 25 are being multiplied by the same binomial. So here I can factor out a squared minus 25 and a plus 6. Now from here I see that I have a special polynomial pattern that's resulting. I can see a squared minus 25, and I know from the patterns that we discovered earlier this week that this can be rewritten as a minus 5 times a plus 5, so that's that part underlined in blue, rewritten there. And then I have the a plus 6 still off to the side. So this particular polynomial, similar to the ones before it, applies two strategies at once. You factor by grouping, and then you expand it a little bit further by using one of your special properties to factor a little bit further.